Welcome to this lecture series in group theory. We're starting a new module which will actually be about groups. The previous module was about elementary number theoretic preliminaries, which we covered because we want to always keep an eye out for number theoretic results. Basically, we'll prove some number theoretic results using group theoretic machinery. Anyway, so what is a group supposed to be? So a group is supposed to be the set of symmetries of some mathematical object. Now, it's not clear what I mean by symmetries. That's not what I mean. Right now, it's not clear, and we'll see more about this particular statement. But for now, this is the best I can say. This is the motivation for the notion of groups, and just hold that thought. And we'll get back to it. All right. So before we define what a group is, let me define what a binary operation is. So S be any set, some non-empty set, then a binary operation on S is any map of this form. So it consumes a pair of elements from S and outputs an element in S. Okay. So it could be denoted by F or whatever, but usually we use a star to denote it. And instead of writing star A comma B, we write A star B. This is a more natural way to write it. Okay, and let us see at least one example. So this addition function, which takes two real numbers and outputs a real number, is a binary operation. So addition of 2 plus 3. Addition of 2 comma 3 is 5, because 2 plus 3 is 5, and we do not write it as such, we write it as 2 plus 3. So we basically generalized this guy. You could think of it that way. Binary operation is a very far-reaching generalization of just the addition on real numbers. You can think of it that way. But binary means 2, so it basically coming from the phraseology is coming from that. It takes two elements of S and produces a single element of S, so that's why binary operation. You can also define ternary operations, but we don't need to talk about them. So finally, what is a group? So a group is a pair where G is just any set, some non-empty set, and star is a binary operation on G. So which of course means that star is a function from G cross G to G. So a group is just a pair of such things such that some properties are satisfied. So first property is associativity, which says what? Which says that A star B star C equals A star B star C for all A comma B comma C in G. So it just doesn't matter in which order you compute this guy. For instance, you can think about real numbers. So in real numbers, if let's say, for instance, 2 plus 3 plus 5, this thing is same as 2 plus 3 plus 5. So we have abstracted this particular property out. Okay? So that's associativity property. Identity. Identity insists that there is an element E in G such that E star X equals X star E equals X for all X in G. Okay? So this is like the zero of real numbers. So in real numbers, what happens is 0 plus whatever real number you want, alpha equals alpha plus 0 equals alpha for all alpha in R. So so this thing kind of abstracts that particular thing out. And let me also prove immediately that this guy is unique. We insist only on its existence, but it follows that that guy is unique because if E and E prime in G satisfy E star x equals x star E equals x for all x, and E prime star x equals x star E prime equals x for all x, then we want to show that E equals E prime. Then in particular, E star E prime, think of E prime as x, equals E prime. Just think of E prime as x and you'll get that. And now let's come here. Think of E as x. So we get E prime star E equals E, which is also equal to E star E prime. So I just, in this equation, I just substituted x equals E and I get that equation. So what we see is that we have this and we have that. But E star E prime and E star E prime are the same thing, so E prime equals E. So in this horrendous green color, I have shown that this guy is actually unique. There is only one such element which satisfies this property, even though we just insisted on its existence. Okay, inverse. It says that for all x in G, there exists some x prime in G such that x star x prime equals x prime star x equals E, where E is the identity. Yeah, so this is called the identity element. Okay, and let me get rid of this horrendous green color, it is bothering me. Yeah, this looks much better. Okay, so this is called the identity of, what color should I use? Let's say orange. Okay. So yeah, so what does the inverse axiom state? It states that for all elements of G, there is some other element of G such that this equation is satisfied. And again, we will show that this guy is unique. So this time I'll not use that bad color. So different. Oops. So if so if let's say x prime and x double prime satisfy these two things, then we want to show that x prime equals x double prime. So how do we do that? Well, we take this first equation. So from the first equation we see that this thing star x double prime equals x double prime star that equals x double prime star E. So what did we do? We just operated x double prime on both sides. Right, so it's like if we have an equation in real numbers, we can just add the same thing on both sides, and that's what we did. We didn't add it, we can't add it. We just starred it on both sides. And now we'll use associativity. So what we get is x double prime star. I think we don't need to use this is fine. So we get that. And the second one I don't think we need to use. So this is equal to x double prime, because x double prime star e is just x double prime. E is the identity, so the above thing is just the below thing. Okay, and what is that? This thing is e because of that equation. So this gives us e star x prime equals x double prime. But e star x prime is what? X prime. Because e is the identity. So we get x prime equals x double prime, and that is what we wanted to show. So this inverse is unique, even though we only insisted on its existence. Okay, so keep this in mind, that the inverse and the identity in a group are unique. Now, before I continue, I need to explain what all these axioms actually mean. This is fine for a formalism, but why should one care? So this is where we get back to the notion of symmetries. Think of G as the collection of all the symmetries of some mathematical object which is hidden from us. And think of star as the operation which kind of composes two symmetries. So if I am given two elements x and y of G, now x is a symmetry of some object and y is a symmetry of the same object. X star y is supposed to mean the application of these two symmetries in succession. So first you apply y and then you apply x. So think of a sphere, and suppose rotations are the set of symmetries that we consider. We can rotate a sphere and we'll again get the same sphere back. So it is the symmetry of the sphere, whatever that means. So if we apply a symmetry, let's say we apply a rotation and then we apply another rotation, that's kind of what this is, x star y. So the result of two successive applications of symmetries is another symmetry, right? So that is what is going on here. So that's the meaning of this symbol, whatever abstract thing this is. Okay, and what is the first axiom saying? It says that, well, you apply these two symmetries first and then you apply this one. That's the same as saying you apply this symmetry and then you apply these two symmetries in succession. So this is kind of, if you think of A, B, C as symmetries, then this is a very meaningful axiom. Okay, what does identity mean? For instance, you take a sphere and you don't do anything to it. You do not rotate it at all. That's like this identity thing. So if you take a symmetry and then apply the identity symmetry, it's just same as saying that you only applied the original symmetry. You did not do anything else, because the identity symmetry doesn't do anything else. So that is what this axiom is abstracting out. So we just, in a very high level, we have abstracted that particular property out. And inverse, so if you apply a symmetry, you can always reverse it. So it's just asking that if there is a symmetry, its inverse symmetry also exists. So if you just undo what you did, you get the identity symmetry back, meaning you get the original position of the object back. So all of this is just, you shouldn't think of a group as the set of rotations or any such thing, but it's a very robust way to generalize that particular notion and many other notions. And that is the power of abstraction, that this is robust. You can apply it in many, many settings where one does not even anticipate that this can be applied. Okay, so that's what a group is all about. And since I've given an abstract definition, I should give examples. But the next 6-7 lectures will be about examples. They will be all about examples. So in this lecture, let me just record some basic properties of groups, even though perhaps at this point it seems super abstract. But let me just do it so that we have a smooth sailing from this point on. And before I get into some properties, let me also give another definition. So an abelian group is a group such that this commutativity axiom is satisfied. So it says that x star y equals y star x for all x and y in the group. So not all groups are abelian, and you can, even rotations of this sphere, you can see that two successive rotations may not commute. It matters in what order you apply the rotations. So before I even say that, perhaps you don't know this, but there is a theorem which dictates that the composition of two rotations is again a rotation in 3 dimensions. So if you take a 2-dimensional sphere in R3, the composition of two rotations is again a rotation. Whatever, if you don't follow that, doesn't matter. Anyway, so here is the thing. We'll introduce a notation and then we'll just prove some basic properties with that notation. So G be a group. Now what does that even mean? So it seems to not mean anything, right? A group was supposed to be a pair. So what do I mean G is a group? Well, this is sort of an abuse of notation, and this will be rampant throughout your mathematical career. Instead of writing G comma star be a group, we suppress this. So this is kind of hidden, the binary operation. Unless we need to make it precise, if there are 2 different binary operations that we are considering on the same set, there is no need to really mention this guy. We even when we, instead of writing a star b, we just write ab. We completely forego writing that thing because it gets cumbersome. So we should get into this habit right from the start, that when I write let G be a group, you should understand that there is some binary operation on it which we just do not write. We can write it, there is nothing wrong in writing it, but we should develop this practice of not writing it most of the times. Okay, so let G be a group and let X be some element of G and N be some integer. Then we define this notation as, or this notation to mean X, well, I'm writing a star but I shouldn't, so let me not. So I'll just simply write a dot. Instead of star, I'll write a dot. So this N times, if N is positive, we define it to be the identity if N is 0. And we define this to be, well, I have to explain this notation also. I kind of forgot about that. If N is negative, and how many times? Absolute value of N times. N is a negative number, so I can't apply it N times. You can't do this negative number of times. So you just take the absolute value and apply X inverse, multiply X inverse with itself N times, or rather absolute value of N times. Okay, so this is the definition, and what is this? This is the inverse of X. So I should have said it right here, that since we've already proven the uniqueness of the inverse of any element, you take an X, there is a unique inverse, we proved it here, so that is denoted by the symbol X and with this. And this is not a foreign notation, this is what we do even in high school when we take the reciprocal of a real number. Okay, so that's what this means. This means the inverse of X in the group G. Okay, so now if G were abelian, we typically do not write X to the N in that way. If G were abelian, we write X to the N as N dot X, or just simply NX, but typically N dot X. Right, so I just wanted to introduce this notation. And now there are some basic properties that this notation follows, which perhaps doesn't even require a proof, but let me at least state the things. So G be a group, again it means G comma star be a group, and X and Y be 2 elements in G. Then first is this power law, which I'm sure you immediately see why this happens. So this I won't justify, the first one. Let me justify the second one. What does it even say? It says that the inverse of X star Y is same as inverse of Y star inverse of X. So proof 1 is an exercise. 2, want to show that the inverse of xy is this guy. So what we really want to show that this equation is satisfied. This is what we want to show. Right? So that's what, I mean, if we show this, then this would mean that this guy is the inverse of that guy. So, but this is very easy using associativity. So if we use associativity, we see this is equal to that. Okay, so instead of writing it that way, so but xy, y inverse, x inverse is x, y inverse, x inverse, which is equal to x e, and yeah, again, instead of writing star, I'm writing dot. Sometimes I don't even write a dot, but sometimes I do write a dot. It's a whim. You can do that anytime. So this is equal to x. Right. So I'm not even writing brackets because of associativity. It doesn't matter how you bracket this. So one does not need to write any brackets. So this since there is an identity here and x times e is just x, so this we are writing that way. So this is equal to e. So what we have shown is this much. Similarly, you can show that guy, and therefore 1 and 2 are satisfied. The third one is also just an exercise. It's purely a matter of definitions. So third one is an exercise. Okay. So these are some basic properties, and then lastly we have some more very simple properties. So again, G be a group, and let A and B be two elements. Then this equation and that equation has a unique solution in the group, meaning there is a unique x in the group which satisfies this equation, and there is a unique y in the group which satisfies that equation. And the proof is very simple. Note that A inverse B, or rather x equals A inverse B, satisfies Ax equals B. So there is a solution. In fact, or rather further, if Ax equals B for some x, then we multiply, or rather we operate by A inverse on both sides, and by associativity we get this is A inverse A, x equals A inverse B, which implies Ex equals A inverse B, which implies x equals A inverse B. So if there is a solution, this is the only solution, and this indeed is the solution. You can easily check that this is a solution to that equation. So we have justified that this has a unique solution in G, and similarly you can do the other part. That's an exercise. It's a very, very similar thing. Okay. Lastly, we have, this is the last property that I want to discuss. And so we have a group G, and we have A, B, U, and Y, 4 elements in G. Then if these two things hold, or okay, forget about it. So I said something wrong. So if this holds, then U equals V, and if that holds, then also U equals V. Okay, so let's do the first one, and second one will be an exercise. So if AU equals AV, then we operate by A inverse on both sides. We use associativity. Which means EU equals EV, but E is the identity, so this means U equals V. As simple as that. And similarly, the second one, and this is called the cancellation property. You can sort of cancel this guy off. You can cancel A off, basically, and cancel B off. And this is what we've been doing since high school, at least in real numbers and complex numbers. If you have an equation like 2 plus 3 equals 2 plus x, you cancel 2 off and you just report that x equals 3. So that's the kind of thing this is. Okay, so let me just write this cancellation property. Okay, so this is the end of the lecture. It may not be clear as to what is the use of such abstraction, but one should just hang tight and one will see some very great applications of these things. It's a beautiful subject, finite group theory. Anyway, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.